right, hello guys. Today we are on 3.4. So we're kind of moving nice and quickly through 3.4. Let me get the guided notes pulled up. And today we are talking about concavity and the second derivative test. So we have a couple of objectives. Do problem set 3.2, 3.3, homework problem set 3.4, lecture will be linked. So before we get into chapter 3, I did a quick before we get into 3.4, I did a quick recap of the chapter 3 vocab we know so far. So this will hopefully help you out when we are asked questions about relative, local, absolute, and global minimums and maximums. So hopefully you can read through that and that makes some sense to you. And now we're going to move into concavity. Part 1. So we already know that the first derivative can tell us about where a function is increasing and decreasing, right? So the first derivative of a function tells us where that initial function is increasing and decreasing. The second derivative can tell us where that, again, initial function is concave up or concave down. And here's a nice little picture to remember. Concave down, frown is how people remember it because, you know, down looks like a frowny face. Concave up, cup, I guess people think that looks like a coffee cup or something. I don't know. However you need to remember it, that's how I remember it. And so concavity is determined by the second derivative of the function. If the second derivative is greater than 0, so in other words, if the second derivative is positive, then the graph of f, initial function, is concave up. If f double prime of x is less than 0, in other words, negative, then the graph of f is concave down. Did I say positive or negative? F double prime of x greater than 0 is positive. F double prime of x less than 0 is negative. I can't remember if I said that right, but points on the graph where the concavity changes are called points of inflection. So that little green guy right there, that would be a point of inflection because that is where our graph changes concavity. So points of inflections are found when the second derivative is equal to 0 or doesn't exist. So points of inflection are essentially the second derivative version of a critical number, right? So critical numbers where the first derivative equals 0 or doesn't exist. Points of inflection are where the second derivative equals 0 or doesn't exist. So we're going to do a quick example about finding points of inflection and determining concavity. So determine the points of inflection and the concavity of the graph of f of x equals x to the fourth minus 4x cubed. So there's our initial function. First derivative is going to equal 4x cubed minus 12x squared. And then I know that I'm dealing with concavity and points of inflection, so I'm going to move right along to my second derivative. F double prime of x equals 12x squared minus 24x. I'm going to factor out a 12x and rewrite this as 12x times x minus 2. And then I want to know where that second derivative equals 0 or doesn't exist. So 0 equals 12x times x minus 2. 12x equals 0 means that x equals 0. X minus 2 equals 0 means that x equals 2. So my two possible points where the concavity could change is at 0 and 2. But what I need to do now is make a little sign chart like I do when I use my first derivative increasing and decreasing functions, right? So I know that the domain of this function is going to be negative infinity to infinity, okay? And so now, again, I'm going to break up my little number line with, in this case, not my critical numbers, but my points of inflection. So that's going to be at 0 and 2. And then I want to pick test values again. So something to the left of 0 would be negative 1. So I'm going to test f double prime of negative 1. If I plug in negative 1 to my second derivative, I'll let you do that fun arithmetic on your own, but you should get a positive number. So that's going to be positive. Between 0 and 2, I'm going to try f double prime of 1. And when I plug in 1 to my second derivative, I'll let you again have fun with that math. You get a negative number. And then to the right of 2, I'm going to try f double prime of 3. And again, when you plug that in, you get a positive number. So looking at this, this tells us that on the interval from negative infinity, that was a weird infinity sign, to 0, since I have a positive second derivative, that tells me concave up. From 0 to 2, I have a negative. That tells me concave down. And then from 2 to infinity, that's again back to positive. That tells me concave up. And then further, since I have a switch in concavity between at my point x equals 0 and x equals 2, further, I now know that I have 2 points of inflection, and those are at x equals 0 and x equals 2. So x equals 2, x equals 0 points of inflection. So, I mean, I kind of have a spread out answer here, but here's my points of inflection, and here's my concavity. So finding points of inflection and concavity is literally the exact same as finding increasing and decreasing function and points and critical numbers, except for now we're dealing with our second derivative instead of our first derivative. And so just like when we went from increasing function to the first derivative test, we're going to go from concavity to the second derivative test. So the second derivative test tells us that if we have a function such that f prime of c equals 0, so that is telling us critical number, right? Because derivative equal to 0 means critical number. And the second derivative exists, so you can find a second derivative, if f double prime of c. So that's saying if you plug in one of your critical numbers to your second derivative. F double prime of c is f double prime of critical number, which you get from plugging your first derivative into 0. So if f double prime of your critical number is positive, then that means you have a relative minimum. Relative min. If f double prime of a critical number gives you a negative number, then you have a relative max. So that's a little bit counterintuitive, but that is what the second derivative test tells us. And this is confusing, but both the first and second derivative tests are for relative extrema. So they're for relative mins and maxes. They both tests are for the same thing. The second derivative test is not for concavity. The second derivative tells us about concavity, but the second derivative test tells us about relative mins and maxes, just in the same way that the first derivative test tells us about relative min and maxes. And then if you plug in your critical number to your second derivative and you get 0, then the test fails and you have to go back to your first derivative test. So here's an example of using the second derivative test. So find the relative extrema for f of x equals negative 3x to the 5th plus 5x cubed. So first derivative, f prime of x equals negative 15x to the 4th plus 15x squared. I'm going to rewrite that as 15x squared times 1 minus x squared, just to factor out that greatest common factor and make it easier for me to find my critical numbers. 0 equals 15x squared times 1 minus x squared, 15x squared equals 0, x equals 0, 1 minus x squared equals 0, x squared equals 1, square root, x equals plus or minus 1. So now I have my critical numbers. Second derivative, f double prime of x is going to equal negative 60x cubed plus 30x. I'm going to go ahead and factor out my greatest common factor of 30x, and I'm going to rewrite this as 30x times negative 2x squared plus 1. Okay, points of inflection. I actually don't need to know the points of inflection or the concavity for this problem, so you can find those if you want to, but you don't need to, because for the second derivative test, we know that we just go ahead and plug in our critical numbers, which are x equals 0, x equals 1, x equals negative 1, to our second derivative. So f double prime of 0, if we plug in 0, we're going to get 30 times 0 times negative 2 times 0 plus 1, so we get 0 times 0 equals 0. So that has failed. So f double prime of 0 fails. F double prime of 1 equals 30 times 1 times negative 2 times 1 squared plus 1. That's going to give me negative 30. So that's a negative number. So since f double prime of 1 is less than 0, that implies that I have a relative max. F double prime of negative 1 equals 30 times negative 1 times negative 2 times negative 1 squared plus 1 gives me positive 30. So then f double prime of negative 1 is greater than 0, which implies a relative min. And then, since f double prime of 0 fails, I'm going to have to go back and use my first derivative test. So, right, so that's going to be, I need to create my number line. 0 is here. I need to test the value on the left and the right. And it ends up that the first derivative is increasing on both sides of x equals 0. So x equals 0 is not a relative min or max. It's nothing. So now our final answer is going to be that find the relative extrema for f of x equals negative 3x to the fifth plus 5x cubed. We have a relative max at x equals 1 and a relative min at x equals negative 1. So that is how you use the second derivative test. And now, moving on, we have this handy little chart for graphical analysis. So you can go ahead and read through these. If you have any questions, bring them to class. Hopefully this is pretty straightforward. It's kind of consolidating what we have done in 3.3 and 3.4 with the first derivative test and increasing functions, and now the second derivative test in concavity, and kind of consolidates it into a nice little table that hopefully you can reference if you need to. So that is all I have for 3.4. Please bring any questions you have to class or tutorial or anytime, and I will see you in class. Thanks, guys.